Scientific discovery by generating counterfactuals using image translations. With success of visual models in medical applications, model explanation plays a critical role in validating whether a model conforms to how doctors evaluate these images. In this work, we want to go a step further to discover the underlying properties of the data or phenomenon itself. What do we mean by discovery? Specifically, we want to identify what the model is looking at and potentially exaggerate it to learn a simple set of features or properties to enable experts to perform better or improve our understanding of the disease. In this work, we look at the task of diabetic macular edema, which often results in vision loss and is characterized by retinal thickening in the macula. The diagnosis for DME is based on fundus images, here shown on the right. This has over an 80% false positive rate and is then confirmed using a 3D scan via optical coherence tomography or OCT, which would be 10 times more expensive. But from the OCT slice, the retinal thickening can be very easily observed. Here are a couple of examples. The one on top has DME, and the retinal thickening can be observed in the OCT slice. The slice corresponds to this particular slice here in the fundus image. And here is a healthy eye at the bottom, where looking at this particular slice, we see the center slice of the OCT. The foveal dip can be observed, which indicates this is a very healthy retina. Previous work has found that when convolutional models are trained on labels from specialists looking at fundus images, the performance of these models matches that of specialists. But in general, it's quite poor. This is characterized by this green curve here. This is a CNN model trained on labels from specialists looking at fundus images. And this is the performance of specialists on fundus images. However, when the same model with the same architecture is trained on labels from specialists looking at the 3D scans, the model performs much better. Note that the training input images, which are still the fundus images, the only thing that is changing is the labels. And the model performs significantly better. And this is the gap that we want to explain. The first thing we did was to examine if the signal was associated with a specific region. For example, is it associated with the optic disc, or the fovea, or the macula? To do this, we trained separate models from crops extracted from these surrounding regions, both from the optic disc and the fovea. These graphs show the performance of the models on the different crops. We found that the fovea model, here on the right, performed quite well even when it was looking at a very small region. It's just looking at a 0.5 disc diameter, and it performed considerably well compared to the full model that's looking at the entire image. Results from saliency maps using gradient-based techniques are also relevant and show where the model is looking, but not what about these regions are interesting. For example, here in the middle column is the CNN model trained on specialists looking at the 2D fundus images. And this model tends to focus on these yellow lesions present in the retina. The last column here shows the model that's trained on labels from the 3D scans. And this model tends to focus primarily around the macula. So the next question that we want to ask is, what is different about these regions? Specifically, we want to answer the question, what would this fundus image look like if it had DME, and vice versa? To do this, we trained an image-to-image translation model, specifically a cycleGAN, to translate images from one domain to another. Here, for example, from horses to zebras. The cycleGAN model incorporates a cycle consistency loss, which essentially means that when an image is translated from a domain X to a domain Y, and then translated back to the same domain X, then the original input and the generated X should be identical. This is termed the cycle consistency loss. We use cycleGANs with a couple of minor modifications. Specifically, we add a 1 by 1 convolution and also a residual connection, we should make it easy for the model to copy less relevant information. That is, things such as the background should remain unchanged. We then use these models to train from a no DME image to one with DME and vice versa, and apply it to the regions extracted from the macula. We then used an independently trained classifier to verify that these GAN models can convincingly fool the classifier. This helps us verify that the GAN model is faithful to the classifier. Essentially, when the cycleGAN transformation is applied to a no DME image, the output of the classifier flips to that of DME with repeated transformation. And here on the right, in the case of a DME image, we can see that the model classifies the transformed image as no DME. The table here essentially quantifies this over multiple images. Retina specialists observed several such transformations and identified two key features that the model is looking at. Here are a few examples for the no DME to DME transformation. And we can observe that the model tends to add yellow lesions. So there are no yellow lesions here. And as we apply the transformation to make these no DME images to DME, we see that the model adds yellow lesions. And here, from the DME to no DME, it tends to remove these yellow regions. These are known as hard exudates. The model also tends to lighten or darken the fovea, which is very subtle. We then hand engineered features based on these observations to train a simple classifier that fully accounts for the performance of the deep convolutional model. Specifically, we use one binary feature to determine whether or not hard exudates are present in the image. This feature alone gives a performance of about 0.72 to 0.74 AUC, here 74 to 74%. This also gives next, we also compute average intensity values of 10 concentric circles around the fovea and use these 30 features. This gives between 0.72 to 0.76 AUC. Combining both of these features, we get a performance of 0.82, which closely matches that of a deep convolutional model, which is 0.847. That's looking at raw images. Training the deep CNN model to predict other metadata such as gender, etc., lead to the full 90% performance. From this, we believe that the light bounced off differently from the surface of a thicker retina, and a deeper fovea leads to a darker macula, and a flatter fovea leads to a lighter macula. Essentially, we use prediction models and explanations to generate hypotheses that can then be validated, hopefully leading to discoveries. Thank you.